Bismillahirrahmanirrahim. My name is Hira Nadeem. I am student of MS Chemistry Batch 4 from UMT Sialkot, and the topic of my presentation is quantum dots. First, we will talk about the abstract. This note aims to provide a comprehensive understanding of quantum dots, which are one of the most promising nanomaterials in the field of nanotechnology. Quantum dots, also known as artificial atoms, exhibit unique electrical and optical properties due to their nanoscale dimensions and quantum confinement effects. These 5,000 word notes devolves into the fundamental aspects of quantum dots, including their synthesis, properties, applications, and potential future developments. Through exploring the scientific literature and recent advancements, the note highlights the significance of quantum dots in various fields ranging from electronics and optoelectronics to biomedicine and energy. The development of electronics is increasingly dependent on low cost, flexible, solution proceed semiconductors. Colloidal quantum dots are solution processed semiconducting nanocrystals that have a size tunable band gap and can be fabricated on a range of substrates. Here we review developments in colloidal quantum dot electronics, focusing on luminescent optoelectronic memory and thermoelectric devices. We examine the role of surface chemistry in the suppression of non-radioactive processes, the control of light-matter interactions, and the regulation of carrier transport properties. We also highlight the prospects of quantum dots as single photon sources, the design of new classes of colloidal quantum dots and superlattices for emerging applications, and the role of hybrid device architectures in compensating for the limited carrier mobility in colloidal quantum dots solid while maintaining their tunable spectral response. Then we talk about the background. Semiconductor materials feature optical and electronic properties that can be engineered through their composition and crystal structure. The use of semiconductors such as silicon, gallium arsenide, spark technologies from computers and mobile phones to lasers and satellites. Semiconductor quantum dots offer an additional lever because their size is reduced to the nanometer scale in all three dimensions. The restricted electron motion leads to a discrete atom like electronic structure and size dependent energy levels. This enables the design of nanomaterials with widely tunable light absorption, bright emission of pure colors, control over electronic transport, and a wide tuning of chemical and physical functions because of their large surface to volume ratio. Then we talk about its advances. The bright and narrow band light emission of semiconductors, tunable across the visible and near infrared spectrum, is attractive to realize more efficient displays with pure colors. Quantum dots are engineered compositionally and structurally to manipulate energy states and charge interactions, leading to optical gain and lasing relevant to light emission across visible and infrared wavelengths and fiber optic communication. Their tunable surface chemistries allow applications such as optical labels in bioimaging, made possible by tethering quantum dots with protein and antibodies. The manipulation of quantum dot surfaces with capping molecules that have different chemical and physical functions can be tailored to program their assembly into semiconducting solids, increasing conductivity and enabling the transduction of photonic and chemical stimuli into electrical signals. Optoelectronic devices such as transistors and photodetectors lead to cameras sensitive to visible and infrared light. Highly crystalline quantum dots can be grown epitaxially on chosen substrates by using high temperature and vacuum conditions, and their use has led to commercially visible high performance lasers. The advent of colloidal quantum dots, which can be fabricated and processed in solution at mild conditions, enabled large area manufacturing and widened the scope of quantum dot application to markets such as consumer electronics and photovoltaics. Outlook. For a chemistry perspective, further advances in quantum dot fabrication are needed to sustain and improve desired chemical and optoelectronic properties, and to do so with high reproducibility. The entails the use of inexpensive synthesis method and precursors that are able to retain laboratory scale quantum properties to market relevant volumes. A better understanding of the yet incomplete picture of quantum dot surfaces, atomic arrangement, and metastable character is needed to drive further progress. From a regulatory perspective, added attention is needed to achieve high quality materials that do not rely on heavy metals such as cadmium, lead, mercury. The role of nanostructuring in toxicity and life cycle analysis for each application is increasingly important. From a material and photophysics perspective, exciting opportunities remain in understanding and harnessing of electrons in highly confined materials, bridging the gap between mature epitaxial quantum dots and still up and coming colloidal quantum dots. The yet imperfect quality of the latter, a price paid today in exchange for their ease of manufacture, remains a central challenge and must be addressed to achieve further increased performances in devices. From a device perspective, colloidal quantum dots manufacturing must advance to translate from laboratory scale to large area applications such as roll to roll and inkjet printing. Photocatalysis, in which light is used to derive chemical transformations, is an emerging field in which quantum dots are of interest. Quantum information technologies, which rely on the transduction of coherent light and electrons, bring new challenges and opportunities to exploit quantum confinement effects. Moving forward, opportunities remain in the design of quantum dot enabled new device architectures. This is the diagram that show how quantum dots is used in various uh, devices. Semiconductor quantum dot technologies. Quantum dot feature widely tunable and distinctive optical, electrical, chemical, and physical properties. They span energy harvesting, illumination, displays, cameras, sensors, communication, and information technology, biology, and medicine, among others. These have been exploited to realize efficient lasers, displays, biotags, and solar harvesting devices available in the market and are emerging in photovoltaic sensing and quantum information. In quantum confined semiconductor nanostructures, electrons exhibit distinctive behavior compared with that in bulk solids. This enables the design of material with tunable chemical, physical, electrical, and optical properties. Zero dimensional quantum dots offer strong light absorption and bring narrow band emission across the visible and infrared wavelength and have been engineered to exhibit optical gain and losing. These properties are of interest for imaging, solar energy harvesting, displays, and communications. Here we offer an overview of advances in the synthesis and understanding of quantum dot nanomaterials with a focus on colloidal quantum dots and discuss their prospects in technologies such as displays and lighting, lasers, sensing, electronics, solar energy conversion, photocatalysis, and quantum information. Quantum dot quantum confined structure exhibits size dependent electronic properties leading to extra degrees of tunability compared with bulk semiconductors and additional levers in the design of materials and devices. Quantum confinement emerges when electrons are constrained to a domain comparable with their de Broglie wavelength. Quantum confined structure classified as two-dimensional, in which electrons are free to move in two directions, 1D and 0D. These include quantum wells, quantum voids, and quantum dots, respectively. In quantum dots, electrons and holes exhibit a discrete, quantized atom like density of states. As quantum dots become smaller, quantum confinement increases the effective band gap, leading to a blue shift of the absorption and emission spectra. An electron excited across the band gap experiences strong interactions with the remaining valence band hole. Coulomb attraction and spin exchange coupling produce strongly confined electron hole pairs. Under high excitation levels, multiple excitons populate a quantum dot. The close proximity between charge carriers in quantum dots lead to enhanced many-body phenomena that affect their electronic and optoelectric properties. This diagram shows the quantum confinement and fabrication of quantum dot materials. Quantum confinement, leading a size-dependent optical and electrical properties that are distinct from those of parental bulk solids, occurs when the spatial extent of electronic wave functions is smaller than the Bohr excitation diameter. Example of fabrication techniques of zero-D semiconductor nanostructures, including early demonstrations of high-temperature precipitation in molten glasses, top-down lithography, nucleation, and growth of nano-islands through epitaxial layer-by-layer deposition by using molecular beam epitaxy, and solution-based low to moderate temperature colloidal synthesis. Quantum dots were first realized experimentally as glass embedded particles, and shortly after that as chemically synthesized colloidal nanocrystals. Independently, the concept of 3D quantum confinement in semiconductor nanostructures for losing applications was presented and demonstrated by combining a quantum well potential with a high magnetic fields. Quantum confinement, leading to size-dependent optical and electrical properties that are distinct from those of parental bulk solids, occurs when the extent of electronic wave function is smaller than the de Bohr excitation diameter. Functions and assembly of quantum dots. The two main strategies exist to fabricate quantum dots: physical vacuum based method and wet chemical approaches. Top down physical fabrications relies on lithography or milling to define a nanometer sized volume in an existing semiconductor. In bottom up technique, quantum dot growth occurs through assembly of quantum or molecular building blocks, and it is driven by built in strain. MBA and MOCVD have enabled the realization of high-quality epitaxial quantum dots prepared on top of a crystalline substrate. Alternative droplet epitaxial growth of quantum dots occurred through sequential deposition of group 3 and 5 atoms without using lattice mismatch, offering a path towards strain-free quantum dots that is yet to be fulfilled. The chemical solution phase fabrication of colloidal quantum dots is an approach distinct to physical vacuum-based epitaxy. Modern quantum dot synthesis can be traced to the colloidal method introduced in 1993. The synthetic methodology for quantum dots evolved from early work on arrested precipitation of inside small aqueous micelles towards reactions between molecular precursors in organic solvents at mild temperatures 100 degree to 350 degrees Celsius. The nucleation and growth of quantum dot is controlled by surfactant molecules that bind dynamically to quantum dot surfaces. The quality of quantum dots is determined by the crystalline perfection of their cores, the completeness of surface passivation, and uniformity in size and shape. High monodispersity is crucial to retaining the near discrete character of the DOS for an example of quantum dots. Exploration of the synthetic parameter space has led to a continued improvement in quantum dot synthesis, leading to absorption line widths approaching the homogeneous single quantum dot. Doping of quantum dots provide an additional avenue to tune their DOS and type of majority character carrier. The surface ligands in quantum dot, typically bulky organic molecules such as oleic acid and oleamine, introduce repulsive forces between quantum dots dispersed in a solvent, rendering them colloidally stable. Solution-based quantum dot deposition techniques are scalable and well suited for the realization of large area devices. Quantum dot thin film fabrication is compatible with high throughput manufacturing and with variety of substrate which facilitate integration with platforms such as silicon electronics, plastic circuits, fiber optics, and fabrics. Quantum dots from engineered functionalities to applications. The first function is size dependent band gap. The band gap of quantum dots can be size tuned across a wide range of energies from ultraviolet to infrared. The lower bound on Eg is set by the band gap of the parental bulk solid. Control over Eg is central to the quantum dot based technologies, affecting solar energy harvesting, lighting and displays, lasers for telecommunications, sensing, metrology, imaging and medical diagnostic. Narrow line width bright emission. In highly monodispersed quantum dot samples, the discrete atomic-like structure of electronic state leads to a narrow ensemble emission light width of 20 to 80 MeV at room temperature, which approaches a single dot line width. This enables the high color purity needed to reach target performance in next generation displays. Best quantum dot samples also achieve near unity photoluminescence quantum yield, the number of emitted photons per absorbed photon. The narrow band and bright emission of the quantum dots have been exploited in commercial televisions and displays. These features are also of interest for luminescent solar concentrators, devices that act as large area sunlight collectors for PV modules. In Lasing the discrete character of quantum dots electronic states is an important advantage. The sharp DOS concentrators oscillators strength into the desired ground state transition, while a separation between quantized energy levels inhibits thermal depopulation of the emitting band age states. Tunable surface chemistry. Quantum dots feature a large surface to volume ratio, making them sensitive to their environment. In quantum dots, the surfaces are typically terminated with molecules or ions with different morphologies and functional groups. This offers a route to manipulate quantum dot interactions with their environment. Quantum dots can be tethered to proteins, antibodies, or to other biological species and used as optically addressable biolabels. Surface programming offers an additional tool for manipulating energy levels and driving the assembly of quantum dots into conductive semiconductor solids. Ligand exchange strategies seek to replace bulky molecules with shorter, more conductive ligands to enhance interdot coupling and facilitate charge transport. This process can be carried out while the quantum dots are in a liquid solution. It is necessary that these steps do not distort electronic surface passivation so as to prevent formation of intra-gap states that would compromise electronic and optical properties. Tunable charge transport. The ability of quantum dot assemblies to pass current is determined by the ability of charge carrier to cross interparticle barriers. Quantum dot solid exhibit modest charge carrier mobilities, typically below 10 raised to power minus 1 centimeter square, compared with